Hi, Prof. I'm Yin Hao from Group 3, and along with me, we have Cheng Xin, Noel, Zizheng, and Jing Wen. Our group will be focusing on telemedicine. Telemedicine is becoming more important in the context of the current pandemic to meet the needs of those with COVID-19 infection, with medicine promptly delivered shortly after consultation via video conferencing. Although the convenience and speed of telemedicine appears ideal, there are still some areas of improvement. Some of the key impediments of telemedicine includes concern over effective care, privacy and confidentiality, and logistical challenges. Our proposal seeks to utilize data model to create time series analysis of common illnesses across the year to better prepare medicinal stocks, CNN to determine patient sickness based on facial expression, K-means clustering for logistic analysis, web scraping and sentiment analysis to enhance customer service, cost and benefit analysis, and finally, data visualization for telemedicine analytics. Now, Cheng Xin will be talking more on the time series analysis that our group has done.
Hello, my name is Cheng Xin, and I'm going to introduce our time series model and its implementation in the telemedicine industry. The objective here is to analyze and focus the time series of medicine's demand based on its sales data. With this prediction, we want to recommend a better procurement plan for hospitals and clinics and a better sales strategy for pharmacies. Currently, the demand forecasting in pharmaceutical industry is mostly done by using naive model, such as using the historical mean to predict. We want to see whether our time series model would outperform the naive method, since our model would consider both trend and seasonality. Our initial dataset consisted of 600,000 transactional data collected from 2014 to 2019, including date, time, medicine name, and sold quantity. After doing some research, these medicines are categorized into 8 categories, so we have 8 time series. The pre-processing of data includes outlier detection and treatment and missing data imputation. We used the last year's data to be our test set, and we built 2 models, ARIMA and LSTM, and we used 2 forecasting methods. The first is rolling window for short-term forecasting, and the second is long-term forecasting. We also set the key performance indicator to be the mean squared error to compare performance. Then I'll talk about some major findings. First, seaborne box plot confirmed the seasonality for some categories of medicine. Also, some categories has more outliers than the others, indicating that they might be harder to predict. Next, the rolling mean and rolling standard deviation shows the trend at a larger scale. Also, trends and seasonality are explored in time series decomposition. The higher the residue, the harder it is for us to predict. Then we analyzed the stationarity using the augmented Dickey-Fuller test. In these 8 time series, those that fail to reject the null hypothesis are considered to be not stationary. So we need to take the difference or the log transformation to convert them into stationary time series. We further analyzed the autocorrelation and partial autocorrelation via correlogram. Minor autocorrelation is observed at ACF and PACF for some series. Some series also exhibit annual seasonality. The first model we built is the naive forecasting, which is our baseline. Then we built the ARIMA model. First, we train the model and use grid search in cross validation to find our optimal parameters for the autoregressive term, moving average term, and integration term. Then we use these optimal parameters for training, for predicting. Then we import LSTM from Python's TensorFlow package. In LSTM, we use the value activation function, and the optimizer was Adam, and loss function was mean squared error. The best results were achieved with training the model in 400 epochs. Before fitting, all data was standardized and transformed to data for supervised problem. Finally, we compare these models by their mean squared error. The result shows that both ARIMA and LSTM performed better than naive methods, which indicates that our time series model would provide useful information. And finally, since the model we built is univariate time series model, and it's likely that the focus would be improved if we expand the problem to be multivariate time series model. So we provide some suggestions for explanatory X variables here. The first is weather data. Since in extreme weathers, the people would cause illness in people and people would want to procure more medicines. And the second is the price of medicine, since a discount would also make the demand of medicine spike. And the third and the fourth, days of pension payoff and national holidays, they follow the similar pattern and would cause demand for medicine. That's the end of my time series part. Thank you.
Hi, my name is Noel. We also discussed how to make use of the image or video data we would have during telemedicine. While researching this, we could find that there are many similar problems and solutions with this. Let me introduce this. In deep learning, a convolutional neural network called CNN is a class of deep neural network that are typically used to recognize patterns present in image, but they are also used for computer vision and signal processing. What happened in these convolutional layers are very similar with the way we process the signal with filters. However, what's important here is that it's just a way to convert image or unstructured data to the numbers or vectors that machine can process further. Changing from offline to online medicine means that data could have disappeared in the offline could be accumulated. Among the truth of data accumulated, especially speech and image data, including natural language data converted from the speech data, can improve the data analytics system a lot. Especially since we can record our videos while doing telemedicine, some will think of processing and analyzing the video itself as priority. If we could be sure what we want to find through video analysis, this could be true. However, video analysis is a task that requires a tremendous amount of computing resources at time. At this first stage of telemedicine we are facing now, it is hard to clarify what we really want to get through the video analysis, even by using resources, a lot of resources. Therefore, we have decided to make an analytic system only with images, which we can get by capturing the video. First and foremost, developing telemedicine itself will be important to develop useful diagnosis technology. In the normal telemedicine system, patients could enter things like CT and X-ray into telemedicine system and apply for medical treatment with it. As telemedicine become popular with the common masses, the system will store more and more CT and X-ray data. What is important here is that when the doctor faces the patient directly, doctors diagnose the disease with diverse factors, including complexions and smells. However, for doctors in telemedicine, the various non-verbal diagnosis features cannot be caught by doctors. In this context, we could consider using not only medical data such as CT and X-ray, but also patient's appearance and screen to fully use the data we have. So we decided to capture the patient during the telemedicine process and use this feature to improve the diagnostic assistance system. In diagnosing a specific disease as well as X-ray and CT, we will feature the patient's face capture photo together. When training the machine learning model to make the system, these two features will be processed through the convolutional layer to make these two information as a numerical vectors each. Then two vectors will be concatenated and put into the deep learning layer. Here, each output of software layer indicates last layer. Software layer indicates all names of disease that can be diagnosed through X-ray or CT. The code here is sample model built on the assumption that both images were compressed to 256, 256, and 3. Even though this could not be a SOTA model nowadays, a model called BGG16 was used in this code. However, we don't have to build a model from scratch. We call this kind of model as multi-input convolutional neural network, and there are many kinds of published paper as written in the right side of the slide. Also, they published the codes they had used as open source in GitHub. In those all papers, The authors all used multi-input layers and consolidated those two inputs before the fully connected layer. The structure itself is very intuitive, where each of the two types of photo will be put into the convolution layers, vectorized and concatenated and fully connected. We can make our system with the same architecture with those from the basic and can train our model with our own data to fine-tune. This is all for the CNN architecture we have discussed until now. Next, Yin Hao will talk about logistic analytics.
Thank you, Noel. Hi, Prof. I am Yin Hao, and I will be going through some of the research and analysis done by our group with regards to logistics in pharma supply chain. Some of the AI implemented across these years for logistics will be data robot and Node2Vec. It was reported that the replenishment time for manufacturer to distribution centers averaged 75 days for pharmaceuticals, but 30 days for other industries, thus signaling a need for a more agile pharmaceutical supply chain. Data robot was created based on historical drug delivery information to predict accurately whether a given drug order could be consolidated with other upcoming order to the same location. Data robot is an AI platform that evaluates predictive models in parallel and is powered by open source algorithms. Node2Vec is an AI created to determine the shortest path using deep learning. The idea of Node2Vec is to use a certain number of nodes in the graph as landmarks and compute their distances from the rest of the nodes. Node2Vec will then sample the neighborhood and provide the output for the shortest distance. This helps to ensure effective delivery and optimizing delivery route. In order to further optimize the delivery time, our group proposed to develop an AI to cluster the patients according to where they stay. Through clustering, we'll be able to distinguish whether a particular patient stays closer to distribution center A or B, for instance. The strategy here is to make use of k-mean clustering with k value equals to 4. We have made a tableau visualization based on the dummy dataset that contains patients' names, address, and the date of medical delivery from polyclinics. From there, we'll be able to draw two key insights. Firstly, having 4 medical distribution centers or warehouses located at the cluster centers will be the most optimal. This allows patients to receive their medicine swiftly while keeping the company's capital investment on warehouses low. In addition, we can also observe that cluster 3, the north area, has a relatively smaller cluster and its cluster points are closer to one another compared to the other 3 clusters, which are bigger and more evenly distributed. This implies that the company can invest in a smaller medical warehouse for the north with lesser medical supplies. Finally, we will be examining some of the pros and cons of using k-mean clustering as an AI for pharma logistics. For the advantages, firstly, clustering allows patterns to be distinguished and outline structure which might not have been apparent before. Next, k-means clustering is able to scale to large data set and guarantees conversions. Lastly, k-means clustering is computationally faster and produces tighter clusters than other forms of clustering. Some of the disadvantages include clustering having a larger sample error, which makes it less precise than other methods. Lastly, k-means clustering is also unable to handle outliers and noisy data, which make it unstable or unsuitable for clusters with non-convex shapes. Now, Jing Wen will go through more on the web scraping and sentiment analysis.
Hi, I'll be talking more about web scraping and sentiment analysis for the telemedicine sector. Reforming the telemedicine patient experience by processing and analyzing customer reviews is crucial. At present, feedback forms are attached to the end of the telemedicine call to collect customer reviews. It is well reported that consumers view brands more favorably if a business invites and accepts customer feedback, especially important as a human-centric design supports consumers at the heart of the telemedicine process. In reviewing customer feedback, one can identify words commonly used while determining customer sentiments, which will be useful for the service provider, be it the customer service hotline operator, doctors, and nurses, to understand their strengths and shortcomings. So, this is our process for the data model. Sentiment analysis will be carried out on Google reviews of Dr. Anywhere, categorizing positive, negative, and neutral sentiments, with further analysis using term frequency inverse document frequency, TF-IDF. Web scraping will be used for data collection of the Google reviews. Both web scraping and sentiment analysis can be used by data and business analysts across different telemedicine providers, and its non-specialized analytical technique, unlike NLP for medical notes, for example, renders potential scalability across the entire sector. The use of Google reviews also ensures quality metrics such as freshness and context. After web scraping with Selenium and Parcel and some data cleaning, we have a total of 64 data points for sentiment analysis. With the sentiment intensity analyzer from the NLTK package, there are a total of 27 positive, 24 negative, and 13 neutral reviews. However, upon closer look, most positive reviews are older in timeline, while negative reviews are more frequent in the recent 1 year, even registering a spike in the latest 1 month. Unsurprisingly, the negative reviews have appeared in the time of a COVID-19 case surge in Singapore, where many have opted to use telemedicine and the service has fallen short in meeting the demands of patients in terms of medication delivery and the consultation experience. The word cloud, as you can see on the right, highlights the commonly used words in Dr. Anywhere's Google reviews. Diving deeper with sentiment analysis, we utilize the TF-IDF to quantify the Google reviews. TF measures the frequency of the term occurring, while the IDF determines the importance of the term in the document in general. Frequently occurring terms may have a high frequency but low importance. The TF-IDF will be exported out to an Excel CSV file for further analysis. In analyzing Dr. Anywhere's reviews, the TF-IDF value highlights terms such as terrible, horrible, sarcastic, and rude in high weightage. There are a few positive sentiments such as interesting amid the negative terms, but most positive terms have a lower TF-IDF weightage. The model may be trained and expanded further to include more stock words and text in the future to increase ease of discovering sentiment terms and accuracy in reflecting the telemedicine sector in Singapore. We have decided to use TF-IDF as it is computationally cheap, simple and easy to use with vectorization, and easier for scaling up. However, TF-IDF does have disadvantages, including that it does not carry semantic meaning and account for compound nouns, which are words that should be grouped together like Dr. Anywhere. For future expansion, one may have to weigh other text binding methods such as BERT or word2vec. Next, I'll be handing the time to Zizheng, who will be talking about the cost-benefit analysis of our AI implementations.
Okay, thanks, Jing Wen. And in this part, I'm going to introduce the cost and benefit analysis of this program. And it aims to help stakeholders and investors to understand 5 main questions: the benefit driver, the cost driver, the risk involved, future cash flow, and finally, the sustainability. So let's get started. The first step of performing the cost-benefit analysis is defining a great analysis framework. And as you can see, this is our framework, and it contains both the benefit driver and cost driver in the respective details. And from the next slide, I will elaborate each part. So firstly, as for the benefit, it contains both the tangible and intangible parts. And for the tangible benefits, it includes the new revenue, the cost saving, the time saving through the efficiency or process automation in terms of the employee operation and technology. And as for the intangible benefits, it mainly includes the improvement of brand reputation. And similar to the benefits, cost contains tangible and intangible as well. For the tangible cost, it's mainly about the hardware and software costs, external costs, cloud costs, and labor costs as well. And most of these costs, I have to say, will be invested at the beginning of the program implementation, and the others will be invested in the next months, multiple months or multiple years, based on the investment schedule and the program development. Then is essential for Dr. Anywhere to take these potential risks into consideration as well, since they are the intangible cost. And there are 4 points which could give rise to AI risk and which should be paid attention to as well. As you can see, there are the data difficulties, security snags, technology troubles, and model misbehaving. Then let's move to the cash flow. The cash flow of this program in the next 5 years is shown as this table. And in this table, all of the stuff we mentioned in the last several slides are involved. And these values are the approximate values, predicted based on the market scale of Doctor Anywhere and the development expectation of this program. So then let's go to assess this program from some financial aspects and identify its sustainability. As you can see, there are 3 main financial indicators. Firstly, let's take a look at IRR. As you can see, the IRR of this program is 34.91%, which is quite high. And the payback period is just 2 years. And the NPV of this program is 2,127,000, which is quite a lot of money. So it means that this program is sustainable to a large content and it's a quite good program. So next, let's welcome back Jing Wen to continue her part. Thank you.
For our last analytical technique proposed for the telemedicine sector, I'll be presenting about data visualizations. Data visualization enables a quick understanding of black and white statistics. Furthermore, implementing a dashboard keeps an organization accountable for their data trail while ensuring that the data may be stored and used appropriately, retaining information with minimized privacy risks. For example, one may dispose of the historical data after a certain number of years to reduce data storage while reducing the risk of breaching data policies. A visualization dashboard will be useful in meaningfully understanding day-to-day clinical operations. Our Tableau dashboard presents weekly statistics of infectious diseases, virtual call rate, median and maximum consultation time, and delivery classes, while yearly historical data is reflected for medicinal demand. The above proposed dashboard adopted historical data for the year 2021 in a weekly format as an example to depict the visual. Ideally, the visualization dashboard should include the latest day-to-day data reflecting daily operations. The infectious disease chart includes common diseases such as acute upper respiratory tract infection, acute diarrhea, conjunctivitis, chickenpox, and dengue fever. The median and maximum consultation time and virtual call rate have been tweaked with reference to the Ministry of Health's data reporting to reflect statistics useful in measuring telemedicine operations. Having an overview of daily ground operations, especially for main healthcare groups with numerous clinics around Singapore, such as Fullerton Healthcare and Raffles Medical, will be useful to examine and broadly analyze trends before identifying points to improve business efficiency. Analyses include, if there is a spike in certain daily infectious diseases, the clinics could prepare appropriate medicine and tools to address patients' diseases. If there is a spike in virtual call rates on specific days of the week, the medical group could dispatch more doctors to be on duty on high call days. Tracing the median and maximum consultation time with a box plot will allow clinics to troubleshoot and improve consultation efficiency. And now I conclude. Several techniques such as time series analysis, CNN, k-means clustering, and NLP are proposed to advance the telemedicine sector in Singapore. Besides data collection and deep analysis, data visualization will also improve the state of analytics in the telemedicine sector. Our cost-benefit analysis has shed light on the usefulness of AI in business. Issues across the pipeline may be addressed to advance telemedicine for widespread societal usage and bring Singapore closer to implementing extensive 5G technology in healthcare. Thank you.